All right, I have that it is now 2:30 Pacific time, so we can get started with the session. It is being recorded like all others in the conference, of course. Dan Reichart is going to talk about robotic telescope labs for survey level undergraduates. And I will stop sharing and give him control.
Okay, I'll start sharing. So everyone's still hanging in there, long day. Depends on your time zone. Over here on the East Coast, it's 5:30. I'm ready to call it a day, but we'll do this first. Let me screen share. Okay, and I'll start the PowerPoint. And then I'll flip the screens. Everyone can see that? Okay, so yeah, thumbs up. We'll use some thumbs up today. And yeah, so we're going to talk about our place in space. It's this undergraduate survey level lab curriculum that we've been developing at University of North Carolina since 2008. It's advanced a lot since then. Makes use of our network, our global network of robotic telescopes, the Skynet robotic telescopes. And let me just put up an agenda for this evening's session, or this evening where I am anyway. So first, we're going to make sure you all have your Skynet registrations, and we'll take care of that on the next screen. I'm going to give you all access to the system if you don't have it already. And this way, you'll be able to put in observations both today during the session, but also afterwards. I'm going to give you about 30 minutes of time, and you can just have fun with it with our telescopes around the world. And it's a process where you'll add an email. I have a postdoc monitoring a page, and he'll create the account, and I'll explain it, but it'll take a little bit of time for all those to kick in. So while that's going on, I'll give you some background information, tell you a little bit about the Skynet Telescope Network. I'll overview the curriculum, the Our Place in Space, or OPUS curriculum, briefly. We only have so much time. I'll talk about this grant that we just got. We've been building up to this for multiple years. It's almost $2 million of NSF IUS funding. That's for undergraduate level. And what we're doing with this grant, we're expanding the curriculum to more institutions than ever and more students than ever, but also hoping to carry out the largest survey of robotic telescopes in astronomy education, at least at the undergrad level, maybe at all levels ever done. And by then, all your accounts should be taken care of, and we'll jump into some activities. I'll show you all how to submit a basic observation on Skynet. There are other things you can do, of course, more advanced things. And then we'll do an activity from one of the labs. We'll kind of multi-processor it. It's something that one student would go through a bunch of images and do, but we'll all take an image and crank through it real quick, hopefully, and we'll determine the orbit of Triton going around Neptune using something called Afterglow Access, which is our online web-based image analysis system. And I'll talk more about that too. Okay, so let's make sure everyone's registered. If you were in the session earlier this morning, I think I gave you this link. If you missed it, or if you're not in the session, go ahead to tinyurl.com/Skynet-register. I'm gonna pop over there right now myself. So let me close that down. I'll take you to this sheet right here. It's a Google spreadsheet, and just add your email to the bottom of the list. We have a bunch in here already, and it looks like it may approximately match the number of people who are here, so we might have everyone. If not, there we go, some more being added in. And again, my postdoc is monitoring this, and what will happen is he'll put it into our system, and you'll get an automated email from Skynet, the same kind of email a student would get when we register a full class of students, and it will look something like this. And be on the lookout. I'm going to go over some background stuff while this is taking place. You may have to check your spam folder. If it doesn't appear in the next few minutes, check your spam folder. There'll be a registration key. It's been blacked out here. You just click on this link and type in the key. And I don't know, I've never done it, but it's presumably simple. We've had thousands of students do it. And username, password, and you should be good to go at that point. And with this account, it will come with 30 minutes, as I think I said, of observing time on our telescopes around the world. Now beneath here, this is for later on, just for some standard objects, recommended filters and exposure durations. And it's just there for you to reference if you play later, or maybe when we do our observation with Skynet later today. Let me see, so you're still entering those, and that's good, and I'll let you do that. I'm gonna restart my PowerPoint while you're doing it. Switch the screen. Okay, so first a little bit about Skynet. It's a global network of telescopes. It has, again, headquartered out of University of North Carolina. There are two groupings of telescopes. The prompt telescopes are the ones that my team at UNC have taken charge of. You know, we've built these systems, deployed them around the world. We've generally put them at the highest quality sites or very dark sites. So these are like the guaranteed good telescopes on the system. Our biggest cluster is at Cerro Tololo Inter-American Observatory, which is one of the great observatories on the planet, the US outpost in the Southern Hemisphere. We have 8 telescopes there, sizes ranging from 16 to 40 inches. And we're in the process of building some specialized instrumentation. So not just straight up imaging, but polarimetry and spectrograph that the Chileans are building. So exciting things in the works. We have 2 sites in Australia, one at Siding Spring Observatory, the National Observatory, which was unfortunately destroyed by an electrical happenstance a few years ago. We've raised the money to fix all of the damaged equipment. We're just waiting for COVID to abate because they don't let us Americans out of the country and into most other countries at this point. But we do have another operating telescope at Meckering in the western part of Australia, about 100 kilometers east of Perth, at a very dark site. And this slide's a little old. We now have 2 sites up in the western parts of Canada, dark places outside of Athabasca and Saskatoon. Again, these are the ones that we maintain. And here's just an example. This is the original prompt site. We built a bunch of 16-inch RC optical systems on Paramount MEs. But we've been adding to the site, adding new, larger enclosures, upgrading the telescopes as we can pull it off, raising money here and there. This is a typical system, a 24-inch plane wave. This is an astrophysics mount, but we usually use plane wave mounts nowadays. And then we take these smaller telescopes and push them out to these other sites in Australia and Canada. You know, in the south, that gives us round the clock observing and then also some access to the northern sky. Then we have our partner telescopes, and you'll have access to all these as well. These are people who have come to us with their own system that they built themselves, saying, hey, we combine this mount, this scope, this camera, can you control it? And the answer is yes. We've learned how to control pretty much all types of hardware out there on the market today, all the different error modes, and our system automatically recognizes them and corrects most of them in real time. And this is outdated. There are more of these dots as well. Some of these are quite good, but some of them are lower quality campus observatories, bright sky conditions. So it's a mix. And we have a radio telescope. This is a Green Bank Observatory, 20 meters in diameter, 6 stories tall, 150 tons. And in this survey level undergrad course, the students will be pushing it around, collecting spectra along the plane of the Milky Way, which is pretty cool. My only wish is if I can get a webcam on it so they can watch it move, but webcams make radio noise, so it's kind of tricky. Anyway, those are the telescopes. By now, you should be getting those emails back from my postdoc, and you should be doing the registration in the background as I'm talking. Our mission, a little bit about Skynet's mission, we're split 50-50 between research and education. Research front, we built these telescopes to chase gamma ray bursts, and now we use them to chase gravitational wave events. But since our early days, we've partnered with all sorts of groups to help pay for it all. We study supernovae, young supernovae in particular. We find them, blazars, all stripes of variable stars, solar system objects, transits, occultations, trans-Neptunian, asteroid, the whole gamut. And we publish in peer-reviewed journals every 20 days, not me personally, but users of the Skynet system. And then there are so many more observing reports on top of that. 5 times we cracked into Nature and Science. And we're the leading tracker of NEOs in the Southern Hemisphere, which is also a source of funding from NASA. Now, on the education side, we're very committed to education public engagement. One of the exciting things is students get to use these telescopes right beside the professionals using the same interface, as you'll see. So far, we've served 40,000 students through many, many educational programs, but 3 large ones. There are many small ones we've been involved in and many other small ones we probably aren't even aware of that people are using on the system. And they're for all ages. We've had programs from elementary all the way through graduate school level and then again, professional use. It's a transitional technology. You should be able to start at an early age. A lot of our interfaces work at middle school age, but they're also used by the professionals. The 3 big ones, the 2 middle school projects, each were multi-million-dollar awards from NSF, and now Our Place in Space at the undergrad level. So a little bit about the philosophy of this lab sequence. I took over the undergrad labs at UNC in 2008. And at the time we were doing labs in our planetarium chamber. We have the largest planetarium chamber in the Southeast. The astronauts trained there up through Apollo. Beautiful facility, it's fun. But the labs didn't really overlap with what's taught in Astro 101, 102 lecture. And at night, we had small telescopes and the students would come at night, which they didn't like, usually rained out, clouded out, which they didn't like. And even when it was good, they spent all the time fighting with the telescopes. And the science they were doing was, again, not really consistent with what they were learning about in lecture. And so we made the decision, yeah, astronomy majors and minors should learn how to use telescopes. But for these survey level students, this might be the last class they ever take in science. And so we wanted to get right to the science. And our telescope network facilitates that. It's so easy to put observations in and get data back. Again, middle school students are doing it. But getting images back, that's just half the battle. You then need to be able to do science with them, measure things off of them. And we tried different things like Astro Image J with the astronomy plugin and just ran into problems, particularly our high school users. We couldn't install software on their lockdown systems. So we decided to build our own system called Afterglow, web-based, online, so no software to install, and all improvements we can make server-side transparently. User doesn't even know what's going on, really. It just works better all of a sudden. And they don't even need quality computers. They just need a browser and a good internet connection. The heavy lifting is done on the Skynet side, our server side, and it's directly tied into the database. So they don't have to download and re-upload data. So it seemed a good solution. The original version was based in Flash, which we've now written thanks to one of these large middle school grants. Part of it came to us. It was PI'd by Tim Spuck, a STEM plus C NSF grant. It focused on blind and visually impaired students. So it's now called Afterglow Access, where the access part's for accessibility. The whole thing works with screen readers, and we've introduced sonification and things, and it's moving in the direction for blind students to do astronomy. But that's not today's topic. Current features include image exploration, and you'll see these shortly, like brightness and contrast and zooming in and out, basic stuff like that, measuring angular distances in your image, photometry, including batch photometry of many, many images at once, aligning images, doing arithmetic like stacking them together, which we do with parallax observations, or subtracting them, which we do for supernova discovery. Again, basic sonification. And there are many more features in the works. This is a work in progress. We just opened it to the students this past summer, and so far we've had about 1,000 users. But soon you'll be able to upload images from outside of Skynet and directly access every archive under Skyview Virtual Observatory. Images will be automatically photometrically calibrated, which is pretty cool. And we're adding RGB combination, which is the most requested feature from a lot of our users. And depending on a grant we just put in, really full-blown sonification capabilities. So with these tools, with easy-to-use data acquisition Skynet, easy-to-use analysis Afterglow, we designed these 8 and soon 9 labs, and they are bang for the observing time buck labs. We designed these specifically to scale. So careful choices have been made about the objects we're looking at, the exposure times. And so we can scale, and we've already scaled from hundreds to thousands. And in theory, we could go to tens, even hundreds of thousands of users. That's why NSF's backed us to go to the national level. I won't go through, the whole thing, and they're not all Skynet Labs. A couple of them, a pair of them are traditional Earth and seasons, Hubble's law. We use other things to convey those concepts, but things that they do learn, whether we live in a geocentric versus heliocentric universe, by measuring phases of Venus, determining an orbit of a moon going around a planet to measure the mass of the planet using Newton's form of Kepler's third. We'll do a little bit of that today as a group, measuring distances to objects in the solar system through parallax. I have scopes on both hemispheres, so we can image simultaneously, get parallax measurements, measure distances. They do also stellar parallax to Alpha Centauri, and standard candles to measure, like Arlyres and Cepheids and Type 1As, to measure distances farther and farther out. We repeat the great debate of 1920 about our place in the galaxy and the galaxy's place in the universe. Using our big radio telescope, we determine the rotation curve of the Milky Way and its mass distribution. And there's a new lab that we're adding on multi-messenger astronomy. We've now had one optical counterpart detected to a gravitational wave event, and we are one of the discovery groups, and it's one of our active areas of research. So we're going to build a lab around this funded by a different grant. So this is pretty advanced stuff for a survey level course, but what we found is our interfaces but it's what they're learning in lecture, and typically. And we found our interfaces are so easy that survey level students can do this. We had to rebuild our advanced observing course because they were doing simpler things than the survey students with these technologies in hand. You may have noticed this is really following the cosmic distance ladder, which is how most introductory courses are organized. So we did this, and some pretty remarkable things were immediately apparent. Students were posting their pictures on social media and posting things like most exciting homework anyone will ever do, or pretty damn awesome. So we knew we had tapped into something, and our enrollment numbers verified this. Within 5 years, our enrollments in introductory astronomy courses went up 100%. Now 1 in 5 students at UNC, which is a large school, take introductory astronomy. Our majors, our AstroTrack majors, went up by about 300% out of this increased enrollment. Many came back and became majors or minors, which helped us pave the way and convince our administration to hire 2 more astronomers. So it's been very successful for us. And it's since been latched on to about 15 institutions, 1,500 students per year, and this is growing rapidly. And these last 2 slides are the end of the spiel, and then we'll start to have some fun. So we proposed to NSF to expand this into a national curriculum, given the good things we were seeing, and some preliminary survey work that showed that it was boosting student attitudes across 10 institutions, where we checked like 30 different course components, and Skynet-based labs and instructor quality were the only things boosting student attitudes. So this is a team effort with Tim Spuck, Michael Fitzgerald, David McKinnon, Rachel Freed, and instructors at about 30 institutions, yet we're still bringing in more people, and maybe some of you will be interested in giving this a try. The goal is to get up to 5,000 students per year, so we have a really huge survey sample. And the grant provides for compensation to adopting instructors, both to learn the curriculum and to implement it. And here's a tiny URL showing our fall training. In the falls, we're just at the beginning of this 5-year grant. In the falls, we train the instructors on the labs, doing 1 lab per week over Zoom. And in the spring, it will be feedback, post-implementation. You give us feedback and we'll improve the labs. So there'll be a development cycle. Also, as part of this, instructors carry out pre and post surveys with their students. 1 instrument that measures attitude, self-efficacy, and career intentions, and the other measuring learning gains or content knowledge. And you also host a site visit. One of our education research postdocs will come, do some informal interviews with your students and with you, and observe a lab in action. So it's a pretty in-depth, wide-scale study. Last slide on this. There's been a lot of anecdotal evidence over the years about the power, the positive impacts of using robotic telescopes in education. But this, we're really going to put it on a formal setting here. As I said, it may be the largest study yet done. And the educational researchers have a whole host of questions, but here are kind of two key ones to me anyway, my observations, and they'll verify or deny with their study. But are the students getting excited because they feel they're collecting real data with real scopes used by real scientists doing real science? Many of you are familiar with the CURES, course-based undergraduate research experiences, where you try to get in the classroom setting, them doing research. And here we're not doing research, we're doing like the greatest hits of the past 400 years, trying to really connect to introductory astronomy curricula. But there's tremendous overlap with the CURES pathway model. They're doing observations on cutting-edge research instrumentation. We sometimes call these CUREs, course-based undergraduate research instrumentation experiences, which is a better acronym in my mind. But there's a lot of overlap, and that may explain part of the success we're seeing. The other aspect is data ownership. Like, I did this myself, and these are mine. Now, last bit here, the labs we partnered with Cengage, which is a national company, actually with WebAssign, which they purchased, and to produce a really quality product. There's a link here for you to preview the PDFs. If you want to view it in the WebAssign environment, you just email me, and I'll get you a free instructor account. I spent the summer filming videos, tons and tons of videos, overview videos, tutorial videos that are now linked in the labs, and they're really popular among the students. Even now, we get about 400 to 500 views per day for 30 to 40 hours watched per day, which is kind of cool. I'm like teaching continuously, even when I'm asleep. Now, it's not free. There is a cost and a sustainability model. WebAssign charges a little bit more than I'd like, $65 per student, but it's a pretty elaborate, interactive lab manual that they've produced. But some of that will come back to Skynet, still settling on how much, and that's our sustainability model. Many of these efforts are born out of enthusiasm and goodwill and energy, which peters out. This is a financial model to keep it running. These telescopes are expensive. Observing time goes for $75 an hour on a standard system, and more on some of our competitors. And this is a way to cover it. Okay, I'm done blathering. Now I'll check out the comments in a little bit, but I want to keep pushing the chat. I'm not looking at it right now. Your turn. So does everyone have their Skynet accounts now? If so, give me a thumbs up. Okay, most of you, and if you don't, just follow along, and it looks like almost all of you have them. So let's go to skynet.unc.edu. It's right here, skynet.unc.edu. You should be able to log in now using your username and password. And if there are any problems, I'm afraid I'm not going to try to troubleshoot in real time, but we'll talk afterwards. But it's pretty straightforward. Again, we sign up over 1,000 students a semester, and it works pretty flawlessly. Once you get in here, I can show you a couple things. I'll show you Skynet Live to start with. This is showing us what's connected right now and what they're all doing. The radio telescope's observing, and it's almost getting dark enough over in my hemisphere. A few more minutes and domes will start opening, and we'll have a number of options. In Chile, the sun's still 6 degrees up. And our telescopes on the other side of the world, let's see, I have one in Poland here, so, but it has bad weather. Anyway, you have a mess. It's a queue-scheduled system. Sometimes things will go through right away. Sometimes you have to wait a little bit. So go to My Observatory and go to Optical Observing. Click on that. There's also radio observing, but I don't think we'll have time for that today. Let's see, this is 5:30 to 6:30. I think we're doing okay. And you'll probably see a blank screen. This is a list of all the observations you've taken, which is probably nothing at the moment. You can see I have pages and pages of them, but let's get something in on this page for you. So go over to Add New Observation, click on this. I'm just showing you how to put in a simple, straightforward observation, and then you can come back later and play with it. A couple ways to do it. We have kind of planetarium software here that you can move around. or just set to right now. Let me change over to, I don't know, some other, well, I'll leave it here. I'm in the Southern Hemisphere in Australia. I'll just go to a dark time here. And, you know, you can pick objects. There are a couple ways you can do it. If you don't know what you want, you can just kind of poke around, zoom into whatever interests you, click, it loads DSS previews. There's a little galaxy. There's a prettier galaxy. Maybe I'll observe that one. You could also, I don't know, well, you can also use keyword lookup. Maybe I'll type in the moon and I'll zoom out. And there it is, the moon there. And you can zoom in with the moon. And you can actually carefully place, you know, on the terminator if you want the field of view of your telescope. Anyway, I think I'll go with the Tarantula Nebula. It's a good Southern Hemisphere source. My best telescopes are in the Southern Hemisphere, but you pick whatever you want. I was looking at M1, the Crab Nebula, shortly before you got here. So I've chosen the Tarantula Nebula. I looked it up and found it. Here's the name. You can rename it if you want. Tarantula is awesome. Or for demonstrations, since it's circumpolar, Tarantula is reliable. But it looks up the coordinates and puts them in there. And if you pick a moving object like a planet or an asteroid, it will update that before dispatching it. And then max sun elevation, -18 is standard. Though in the labs, I tell the students -12 is dark enough for their work. I tell them 20 degrees, your target 20 degrees above the horizon is good enough for their work. You can get a few more things through that way. Then with some advanced settings, dithering and stuff like that, you can close that. And here's an air mass chart. I picked a Southern Hemisphere object. And actually, I'm going to change my mind. To demo what I want, I'm going to pick a Northern Hemisphere object. So I have many more telescopes there, but not an open cluster. They're boring. Not even sure what that is. It's got to be a glob in here somewhere. Or a galaxy. It's a bright star. I'm just having gotta be galaxies in there. Okay, something in the Northern Hemisphere. So you see many more sites since I have many more telescopes in the Northern Hemisphere. Just gotta make sure that something is above the gray line at some point in the next 24 hours. When you get here, and it's observable in the next 24 hours, select choose filters, and I'll pause and I'll wait for you to put the thumbs up again to make sure everyone's at that point. Some of you have gotten there, some of you are deciding on your object, but of course they're, you know, I've given you 1,800 observing credits, so you can keep coming back after the fact and hit all your favorite things. Okay, I think I'm getting mostly thumbs up at this point. So this next page is you pick your filter. And we have every filter system you can imagine in here. Some of our prompt telescopes have custom filter wheels with 17 slots, so we can accommodate many filter systems on a single scope. Got like Johnson Cousins here. It's an accordion format kind of thing. Astrophotography filters, narrowband, Sloan. Up here, I have some generic ones that can be pretty useful. High through corresponds to an open or a clear or a luminance or anything that lets through a lot of light. Low through could be a narrow band or U band, anything that lets through a very small amount of light. You can see as I click these, some of my telescopes, these are all the telescopes that could observe that object, but some of them got X'd out because they didn't have that filter. As long as you have a handful of scopes that can do it, you're good. I'm going to go with high through because I picked a galaxy. You tend to want to bring a lot of light in there. Only one scope doesn't have a high through. Save and continue. Next, we'll pick our telescopes. Now in the labs, I tell the students, if you have plenty of time before it's due, just go with the prompt telescopes. They're guaranteed to be the highest quality. We have some of them here in Chile. Here's one in Australia. Here's one in Canada. And you can click all of those. Or you can click on the little orange button under your time account. Most of you probably only have one time account, and it's full of all the telescopes that have been COVID recovered, that have reopened since COVID began. And as more reopen, I'll stick more into that time account. If you just click the orange button, it selects everything in that time account for you. Kind of quick and easy. I think I'll do that. That means some includes our good telescopes and our lesser telescopes. Save and continue. And then we'll get to the observation design page. And I'll pause again and I'll wait for the thumbs to make sure everyone's with me here. So you're picking a filter, you're picking a bunch of telescopes. Don't just pick one telescope. That's a mistake students make. They say, I want this telescope, and it goes down for maintenance or something breaks on it and they're waiting for months. You pick a lot of telescopes, it's going to go through somewhere quickly. And that's one of the great advantages of a global network for education. Okay, now this is tricky. I have a very heterogeneous network. Some are big, some are small, some are good sites, some are not as good sites. So how do we put in a single observation that works for all these different types of telescopes? Well, you pick a design telescope and my recommendation is pick the generic 16-inch. It's the same as our Prompt 5 telescope at Cerro Tololo. So it's a 16-inch telescope at a great site. And the labs are built around this telescope. But as you'll see, it still works for all scopes. So I'm going to do one, 80-second exposure, usually for galaxies, bright galaxies, messy objects, 40, 80 seconds is good. If you picked a planet, you may want to do 1 second or 1/10 of a second in the low-through filter. It varies. And I gave recommendations on that Google Doc that we were looking at before. As I go from scope to scope, you see that the exposure duration varies. Some are longer, some are shorter, and this is taking into account the quality of the telescope. The thing that's thrown me is if the exposure becomes too long, longer than the max, it should pink out and not let you expose on that telescope. I must have clicked something incorrectly. I'm not sure why it's doing that. But anyway, all these telescopes are then possible. First available is what it will be dispatched on, and it scales the exposure time such that you get the same signal to noise. If it's a low quality telescope, be a longer exposure, a high quality telescope, shorter exposure, but you're still charged the same number of credits. The credits are buying you signal to noise.
Dan?
Yes.
There's a number of questions popping up in the chat you might want to take a look at, or I can read them out loud for you.
Yeah, go ahead if you would.
I'm not sure the best timing, but Diane asked, can you repeat the observatory name? Can you mention the object? Larry wrote, is there an expiration date to our observing period?
Yeah, so let me answer a couple of these. So there is, it's down here under, there, I had to click off it. That's why they didn't go pink. You type it in, you click off, and these observatories were ruled out because their scaled exposure times are longer than that observatory permits to maintain good tracking. Okay, now to answer some of these questions, down under advanced options, you can do things like repeat this observation every hour for however long you want. And there's also a cancel, and it automatically cancels 1 month from today. Now your accounts will stay open, but if you put observations in and they're not observable right now because the sun is up in that part of the sky, after a month, it dequeues itself.
David asks, is one observing credit equals 1 minute? Question mark.
It equals 1 second on that particular telescope, 16-inch telescope in Chile.
Oh, I see. James responded to that. Okay, thank you.
Yeah.
And last question for the moment is Jeffrey asked, does Afterglow Access also work with the diffraction grading?
Yeah, we have a few filters in there that do spread the light, low resolution spectra. We are building, the Chileans are building a formal spectrograph that will go on the 32-inch in Chile, but among the filter options are low power dispersion that would disperse everything in the image. And I should say, it's very nice you're putting things in the chat, but we're a pretty small group and you're welcome to just shout out. I love to have conversation. That way I know whether people are interested or whether I'm boring them to death. It's impossible to tell. But,
yeah, I highly encourage that. That's a good suggestion. It works a whole lot better when there's little more liveliness to this with voices other than just dance. Not that anything dancing wrong. It's just helpful to have that verbal input. So just go ahead and unmute yourself, anyone.
Yeah, and I'll maintain my enthusiasm, assuming that you're all happy. And Greg, if you see anything in the chat, feel free to interrupt if they didn't want to. But anyway, okay, I got mine in there, and I'm not gonna do any of these advanced options. I'm just gonna save and continue. And again, you could pick any object you wanted, any filter, whatever. And these are the telescopes that made all the cuts. They're the right latitudes, they can observe the object, they have the right filter, the exposure duration it's not longer than the maximum permitted for that telescope. And so I'm gonna submit it, and then it's in your list as active. And you may not have anything else in your list, so I'll just call something else up that I've already done. This is the Tarantula Nebula. It was executed by the Prompt 3 telescope, 24-inch in Chile, so a very nice telescope. You can see it got a really nice image. This was high through, this was low through. So you see the difference that came out there. Now this page, you can download the fits if you want. Also, we have master biases, darks, and flats. If you want to do your own reduction, you can use them, or you can download already reduced. Skynet generates the masters automatically. You never have to worry about that. But this is not the interface you'll want to use to analyze the data. This is just to get the data. So if there are no objections, we'll go to Afterglow next. And the link for that is afterglow.skynet.unc.edu. And I'll give you a second to get in there. You'll log in with your same Skynet credentials. If you're already logged into Skynet, it should be simple. If not, it will take you over to Skynet. You log in and it will get you in there. And once you're all in there, give me the thumbs up. And you won't see anything yet. You don't have any images. I have some images preloaded.
So these could be fixed files that we get from anywhere?
Pretty soon. Right now, it's only connected to the Skynet database, but within about a month, maybe 2 at the outside, you'll be able to upload your own images. They'll have to go through an image verification process before we dump them in the database. But we have some funding for that, and so that's being executed. It's a work in progress. There are a bunch of awesome new features coming to it. But again, it's web-based, no software to install. It will also be linked to major archives through the Skyview Virtual Observatory. You'll be able to load anything in from there as well pretty soon. So let's start with how to load something in. If you go to Data Providers and click on View All, you can see what's currently there. And I should say this is the current version on the server. There's also a dev server with all sorts of improvements and bug fixes. And that's in one of the extra Google Docs that I'll link you to. And the dev server will be pushed to the main server sometime later this month. But under Skynet, I can go here, I can go to user observations, and all the observations I ever took are here, so I can go in and grab them. Or going back to the data providers, you know, the archives will be here, there will be a upload your own here, but we have a sample directory. And since most of you don't have any data yet, we'll use the sample directory. I put some stuff in there this morning. If you scroll down to workshop, I have some images there ready for you to go. And let's start with something simple like Jupiter or Saturn. Pick one of those. I'm going to grab Saturn. You just click on it and you import it. It's going into your workbench. And this is like a Google Maps interface. You can zoom into any particular spot, drag it around. I like using a scroll wheel mouse. Sometimes in the labs, I'll have a box of them available for the students, but you can do it other ways as well. There are also buttons here to help with that. And first, let's just do basic, this first tab over here, these buttons are tool tabs. If you go to the first one, it's brightness and contrast. So we have some coarse settings, a faint setting, default, and bright. The bright there, you can see there's Saturn. I'll go back to default. You can also adjust the background level and the saturation level. If I increase this, you see I can decrease the sky glow around Saturn and make it easier to see surrounding moons. And students learn how to do this right in the first lab, and you do moon identification at the same time. They learn how to bring this object up in stellarium, match the time, and figure out what moon's what. Like that's Titan and Rhea and Tethys, Dione. Enceladus is lost in the sky glow. I wasn't able to bring it out. That's got to be a background star. But anyway, that's one of the skills they learn. Many, many skills. I can't go through all of them today. And let's see. So the next thing I want to do is an exercise. Once they learn how to identify moons, we have them take a sequence. They pick a gas giant of their choosing, and they observe it once a day or maybe twice a day for a couple weeks while they're doing labs 1 and 2. And then the data is ready for lab 3. And in lab 3, one of the things they do is they're going to pick a moon, identify it, and measure its distance from the planet sequentially and determine its orbit. And once you determine the orbit, you can figure out the mass of the central body. So let's try doing this as a group. I've never done this before, but let's see how it works. If you go to tinyurl.com/Skynet-Triton, it will take you to a sign-up page. Now, normally the students each collect their own data set and they analyze all the images, but we're time limited. So you're each going to take one. Once you get in there, under your name, claim one of these images. Just type your name in and say, this one's mine. If there are more than 14 of you, then whoever's left over can double check someone else. So again, that was tinyurl.com/Skynet-Triton. Now give this a second to fill up. And of course, we don't have time to collect our own data. I'm going to point you to some archival data, and each of you will load just your particular image. And I think we have some shy people. See, the nice thing, I'm going to treat you like naughty students. I can see your names on Zoom and I cannot see your name here. So you should be embarrassed for yourself then. Anyway, we're getting most of it here. We have about 7 more minutes. So, finish that if you want, and I can fill in the other ones. I did this beforehand to make sure I wasn't going to run into any problems, and I have the data in another tab just in case. So now go back to Afterglow, go to Data Providers Sample Directory, come up to the, oops, I went too far, into the workshop, and then Triton, and find your image, and just match the number you signed up for. I'll click on this one and then import it. You could import all of them, but with all of us hitting the server simultaneously, it can slow it down a little bit. And I picked one that wasn't very good. Some of these are actually quite good, and some are lower quality. And give me the thumbs up once you have your image in there. So I know that we're all ready to make some measurements. Cool. Now back on this page, you see there's telescope name, and there's Julian date, and also the separation. We want to figure out how far is Triton from Neptune as a function of time. Let's start with the telescope name and the Julian date. I'll show you how to get that. So the first, zoom into Neptune. It should be obvious. It's the one that's bigger that has a little dot next to it. The little dot's Triton. You'll find it somewhere on your image. Now, if you go to the next tab down, we can figure out the telescope. And for some reason, it's giving the observatory. It had the telescope this morning, but when we transferred it to the sample directory, something changed. And you can enter that under telescope. It's sometimes good to know what took what. But the key thing is the Julian date. And in the new version, we have that out here on the main page. This is kind of the most important stuff in the image header file, but that's on the dev version. So you all right now have to go into the raw image header That's this first click here. It shows you everything. And then just Control F JD, find Julian date, copy it, and put it in here. I can't remember which one I did. See, I did 7. Let's see if someone's doing, yeah, someone's already doing 7. So I'll let Emily do her own there. But we're getting the x-axis fleshed out here, which is good. Okay, now let's do the measurement. Oops, sorry. So for the measurement, go down to the ruler tool. Oops. 2 more steps below. And click on centroid clicks. You could do it by eye if you wanted to, but the centroid clicks is nice. Now there are different centroiding algorithms for point sources and planets. So I would click on the moon first, anywhere close to the center, and it will centroid it perfectly. And then come over, oh, I guess my planet clicks was already turned on. I'm gonna do it again. Let me get this out of the way. So centroid, and then I'm gonna turn on my planet centroiding and click on the middle of the planet. You see it adjusted it to the true middle. And then down here under separation, grab the separation in arc seconds. Control C, and then you paste it over here. While you're doing that, oops, I have my cheat sheet over here on the other window, and I'm gonna grab the ones you didn't do and fill them in for you. Let's see, 19 and 21. And let's see, 7. And it's interesting, some of them are posting as numbers and some are posting as not numbers, I think. So we'll see how this copy and pastes over. We'll find out in a second. I think this is everything. So I'm just gonna paste as values to get everything into a numerical format. Sometimes when you copy and paste, if it posts as a string, then it's not gonna copy next into the thing that we're gonna copy to next. So now, very quickly, we just did all of our measurements. So copy these, and I have another tiny URL for you, tinyurl.com/Skynet.graph. tinyurl.com/Skynet.graph. This is a custom graphing application that we built just for this lab course. And it has some pretty cool things here. The first one's just basic graphing. Let's go to the next one. Under the options, select moon.
You got about 2 minutes left, Dan.
Okay, I think we'll be able to hit our mark here. So copy out that junk data and paste in the data that we just took as a group. Okay, and what we're plotting here on the x-axis is Julian date. The y-axis, this is angular separation in arc seconds. So you can see it's very easy for students to add titles and axis labels. And now we're gonna do chi by eye. We're gonna fit this model. This is a model of a moon moving away from a planet and crossing it, and moving away on the other side and crossing it. So you can follow along. First, I'm gonna shrink the semi-major axis to kind of touch the top ones. And with Neptune, it's not edge on, it's face on. We're watching the moon go around. And so we have to do a tilt. It will never cross in front of the planet. Then I adjust the phase to try to get it to touch that first point. And then play with the period. This is the tough one, but get it down there and eventually things will look like they fit really well. Around 5.8 days. It takes a little bit of getting used to. You may have to adjust the phase again. And you can play with it. Given our lack of time, I'm not, but we just determined the orbit. We got the semi-major axis, the period, with a little bit of manipulations, you can get the mass. And I'm just gonna end by showing you some of the other cool features here. In one lab, we determined whether we live in a heliocentric or geocentric universe by plotting phase of Venus versus size of Venus. Heliocentric universe measurements land on this curve, geo in the blue curve, and it's explained in the lab why. Variable stars, let me just upload a data file here. Pick one of these. This is an R-Lyrae star, variable star and a reference. So you pick the R-Lyrae star, put in the magnitude of the reference star to calibrate the scale. We have a periodogram. They don't really have to know what it means. You find the highest point. This is oscillating on a period of 0.33 days. So you can go to period folding and period folded light curves to establish standard candles, R-Lyraes, Cepheids. One last one I'll show, and then I'm out of time.
Yeah, but we're over time now, so just, yeah, try to wrap it up.
Okay, this is the last one. This is the great debate. And so there's a lab where now that they know how to do Cepheids, sorry, I have it on my other screen, or R-Lyraes, we have them do them for 30 globular clusters, the distance. And so I'm going to copy out this junk data, put in the longitude, latitude, and distance, and this makes a top-down projection. So you see where the sun is in the Milky Way. We're not at the center. You can measure the size of the Milky Way, and so forth and so on. So you can do lots of things. And so I will just end by putting up my final slide, which is a link to additional information. All these links and additional links are under tinyurl.com, Skynet/links, or you can email me directly. And again, we're looking for instructors who are interested in implementing this, and there's funding for your time and energy to implement it, to survey it, and help us make it better. Okay, sorry for going a few minutes over.
Thanks, Dan. All right. We have another concurrent session, two more this afternoon or evening, depending on your time zone. So we'll see you all real soon. Thanks, everybody.
Thanks.
Thanks, Dan. Bye.
My pleasure.
Yeah, thanks again, Dan. That's great stuff. Great stuff.
Great to see you again. I'll see you next semester, I'm sure.
All right.
Okay, signing off.